Hey everyone, welcome back. Today we're going to be doing something a little bit different, something that I think is pretty fun and exciting, which is we're going to be looking at a new computer, which is the Commander X16 computer. Well, actually we're not going to be looking at the specific computer itself, but rather we're going to be setting up a development environment to help us create assembly language programs for the Commander X16. Now, if you found this video, you're probably already familiar with the Commander X16 computer, which is a new computer being developed by the 8-bit guy David Murray and some of his friends. So at the time of this recording, the main circuit board, I believe, is pretty much completed. It's been distributed, I think, to a few key developers to do some final testing and work out some final bugs. And then after that, they're going to make it available to the general public for purchase. And I think the plan after that is to actually develop some further versions of this computer, making them smaller and replacing some of the through-hole components with surface mount. But of course, first the initial version needs to be a success once it gets released. So the development environment for programming an assembly language for this computer can be a bit tricky to set up. And so today I'm going to share with you the method that I was able to use to get it working on my computer. And the development environment I'll be setting up today is going to be on a Windows PC. And I'm going to share with you the tools that I used and the method that I used. And we're going to take a look at some of the more interesting aspects of these tools so we can become more familiar with it and be more comfortable with them when we go to actually create some programs for this computer. So today's video is going to be probably a bit long. We're going to get into some fun details looking at these different tools. But if you're interested in creating assembly language programs for the Commander X16 when it finally comes out, then stick around and we'll get into it right now. All right, so let's start off by taking a look at the computer itself. And this is a picture that I found online of kind of a sample case that was made up by, I think, a YouTube presenter called Perifractic, if I'm getting that name correct. He has videos on YouTube that show this case, and I'll try and put a link to one of his videos in the video description down below. And the computer, I believe, will not be initially shipping with any case. I think it will probably ship with a keyboard, but I don't think it's going to be shipping with a case, although perhaps the cases will be available separately. I don't know. Hopefully it comes with a case because I think it'll make it a lot more popular if it does come with a case. But in any rate, this is kind of a mock-up of what the computer could potentially look like once a case has been developed for it. And let's just go through some of the general specifications for it here. You can see at the top it's listed 65CO2 processor at 8 megahertz. So this computer uses a 65CO2 processor, which of course is based on the 65O2 processor. And that alone is pretty interesting and exciting because particularly for beginners, I think it's going to be a very welcoming computer for people just starting out learning assembly language, because the 6502 processor has a couple advantages over other processors in comparison, for example, to the Z80 microprocessor. The 65CO2 processor has a much reduced register set compared to the Z80, as well as it has fewer commands than the Z80. So I think it's a much easier processor to learn assembly language for than, for example, the Z80 microprocessor. And in addition, this 65CO2 model compared to the 6502 model gives it some more capabilities and some more instructions that make it even easier for us to use and makes it more powerful when we're creating our programs. And as far as performance goes, the 6502 processor is apparently a very efficient processor, meaning you can get more done in your program with fewer commands. It operates more efficiently, or it allows you to program more efficiently than, let's say, the Z80 microprocessor. So if you're comparing the performance between the two processors, apparently a 6502 processor running at 1 megahertz would be maybe on par with a Z80 processor running at about 3.5 megahertz. Maybe not exactly comparable, but in that ballpark. So it's already quite a fast processor because of how efficiently it operates, as well as you can see this computer has it running at 8 megahertz. So this computer is already going to be running pretty fast straight out of the chute. It's going to have this efficient 6502 processor or 65CO2 processor running at 8 megahertz, which should give it some pretty decent speed even running basic programs, let alone the assembly language programs that we're going to be learning how to create starting in today's video. It also will be available with 512K of RAM, expandable up to 2 megs of RAM. And I should say again, at the time of this video recording, the final design for the circuit board, I'm not sure if it's exactly completed. I think it pretty much is nailed down to its final version, but there could always be some changes after this video gets released, so just bear that in mind. But at the time of this recording, these are the current projected specs for this circuit board or this computer. And it's going to be running Microsoft Basic 2.0, which I'm sure probably many of you are familiar with if you've been using the Commodore line of computers up until now as well. It's going to have 4 expansion slots, which is cool if anyone develops any expansion boards for it. It's going to have inputs for both a PS2 keyboard and PS2 mouse, as well as 2 Super Nintendo controllers, as well as 2 internal Super Nintendo controllers. So what that means is there's going to be 2 ports on the outside of the case or on the edge of the board that allows you to directly plug in a Super Nintendo controller, as well as there should be a header on the circuit board inside the computer that would allow you to connect potentially 2 more Nintendo controllers if you were to build a header to connect them. It has some fantastic sound capabilities. It's going to have a Yamaha 2151 sound chip built in, as well as the video circuitry inside this computer, which is a board called the Vera board. It's going to have sound capabilities as well in the form of a 16-channel PSG or programmable sound generator here. And of course the video board is going to give us some video output, and in this case it's going to be in the form of a VGA output video signal. So this would be great if this is what the computer looks like or something similar to this. I'm pretty sure it's going to be a popular computer with an existing community already around it. Of course, the 8-bit guy has a huge following, and so it's always, I think, more exciting to learn to develop for a computer that has an existing community around it that's going to be interested in seeing what new developments people are creating for it. So this is why it looks interesting and exciting for me. Now let's get into the details of exactly how we can set up a development environment to begin creating some programs for it. All right, so the first thing we need to look at is setting up some software or installing some software for it. And before I get into it, I just want to make a note here that the installation instructions that I'm going to be following today are actually based on some instructions that I found online from this 8-bit coding website. And so I'll just share that with you now. So here's the website here. It's called 8bitcoding.com. And on this website, there is an instruction page here that shows and explains how to install and set up the development tools that we're going to be using in today's video. Now, I'm not going to read this word for word. I will put a link to this page in the video description down below, but we're going to go through the main parts of this, and we're going to see how we can install these tools to develop some assembly language programs for the Commander X16. But I am just going to zoom in here and read a part of this. And you can see here this page is titled Assembly in Basic 1, Setting Up the Environment. And if I just start reading here, it says using RetroAssembler and VSCode. So before I get into the details of installing all these tools and setting them up, and these tools are actually not that difficult to set up. If I was able to do it, then that's a good sign for you, because I'm not an expert in configuring computer software and setting up scripts and making all this stuff work together, and I was able to figure it out by following these instructions. So we're going to go through it and take it step by step, and so I'm pretty sure you can figure it out if I was able to figure it out. But I do want to read this first sentence here that says, the goal of this short tutorial is to set up minimal development environment to write and test assembly programs for Commander X16. We will use 2 simple steps to set up our development environment. 1, download and install necessary software, and 2, configure the software for automation. And it says we will be setting up on Windows. So these tools are going to be, as I mentioned before, set up on a Windows computer. And this is true. This is essentially what we'll be doing today. We'll be doing these two steps. Step 1, download and install some software. And step 2, configure the software for automation. So just to give you a kind of a preview of what we're going to be doing, so you are prepared for how this whole process kind of works. When we're creating an assembly language program for the Commander X16, we need 3 basic tools to help us. We need an editor to allow us to actually physically type in our assembly language program. We need an assembler to convert that assembly language program into machine code. And then we need an emulator to run that machine code program so we can test it and see it actually working. So those are the 3 tools we're going to be installing and setting up today. And then near the end of the video, we're actually going to type in a sample program and take a look at some key details we need to be aware of in order to make sure we can get this working properly on our system. So let's go ahead now and I'll show you the checklist that we're going to be following in order to get these tools installed and configured. All right, so back here on my slide, we have a software installation here, and the first thing we already covered is the 8-bit coding setup instructions. We'll be going back and forth between that setup page and this list of instructions as we go through this process. So let's take a look at step number 2 here, which says Commander X16 Emulator. So I'm going to put a link in the video description where you can get the Commander X16 Emulator, and basically you get it from the Commander X16 website, which I'll show you now. All right, so here is the Commander X16 website, and if you want to download the assembler, it looks like there are 2 ways to do it. You can go over here to the left where it says try it online here. I would have assumed that that meant that that would give you access to an online version of the emulator, but when I click on it, it brings me to this page where it lets me, it looks like, download different versions of the emulator. So I would go up here to this Commander X16 Emulator link, which brings me to this page here, and it talks a bit about the emulator, and it should be, yep, right down here. You can see there are files you can download, one for Windows, one for Mac, one for Linux. And so you simply download this zip file and unzip it onto your computer. And if we take a look at my computer, you can see over here I have a Commander X16 folder that I've set up for my Commander X16 tools. And if I open that, inside that you see I have a folder called Emulator. And if I open that, that is where I've unzipped all those files that you download when you go to that website and download the emulator. So it's pretty simple. You just download it, unzip the files into a folder that you want, and that's it. Now if I go back to the Commander 16 homepage again here, you can see over here on the right, there's a link over here as well that says download the emulator to get ready. So there's another link over here that I think takes you to the same place probably. Yep, to allow you to download the emulator. So there are actually 2 links on this Commander X16 homepage to download the emulator, so it should be pretty easy to find. All right, so now that we have the emulator downloaded and installed, well, you don't really need to install it, you just unzip the files basically, and let's test it out and see how we can run it. So here you can see I'm in the folder where I've installed my emulator, in my emulator folder here. And if we look at these files, there should be an exe file right here, x16emu.exe. So the easiest way to actually run this emulator is to simply click on this exe file. And there we go. So it opens the emulator. However, when you do it this way, it opens the emulator without any options selected. It just uses its default options. So you can see here you have a tiny little window, and there are some other options that are also not enabled that we probably want to enable, although you can use the emulator like this if you want. For example, you can type a program here, 10 print hello, 20 go to 10, run, and there you can see it's running our program. So you can use the emulator this way if you like, but a better way to use it would be to create a batch file to allow us to open the emulator using some commands that configure certain aspects about it that make it a bit easier for us to use. So let's go ahead and do that now. Well, actually, I've already done that. And if you're not familiar with creating a batch file, it's very simple. It's essentially a text file. So you would go down to your Windows Notepad and open a Notepad window and then type in the command that opens this emulator. So I've already done that, and you can see right here I have a file called runme.bat. BAT means batch file. So if I right click on this and select edit, we can take a look at my batch file that I created to run this emulator. And so if you want to create your own batch file like this, again, all you need to do is open a Windows Notepad, type in this command or something similar to it based on what options you want to use when you run the emulator, and we're going to go through those in a moment. And then you simply save it with a file name called, well, whatever you want really. My file name is runme.bat. You could use whatever file name you want as long as it has an extension of .bat, which indicates to the computer it's a batch file, which means it will actually execute this command when you activate this file. So let's take a look now at this batch file I've created and what these different options are. But before we do that, let's take a look at the documentation that comes along with the emulator when you install it. So I'll go back to my emulator folder now, right here. So I'm in the emulator folder, and here you can see there's a docs folder. And if I open that up, there are several documents that are included in this folder. So you can see by the titles what they're about. There's documents covering different topics. So let's go to this readme.html file here, and we'll open it up. And here it is here. So this gives us some information about the emulator. But in particular, we can skip most of this stuff and go straight down to right here, this section that says starting. So this tells us some of the options that are available for us when we execute the emulator. So when we create our batch file, we can specify some of these options to start the emulator using particular parameters that we want. So if I go back to my batch file here, you can see the first part of this batch file is simply an instruction that says X16 EMU. And that's the file that we just clicked on to start the emulator. Right here, if we go back to our emulator folder, X16 EMU.exe right here, that is our X16 EMU instruction. So that instruction is going to tell the computer to open this emulator program. And now let's take a look at the different options that I have outlined or specified in this batch file. The first one is scale, actually scale 2. So let's see what scale does. I'll go back to my instruction sheet here, right here, and I'll zoom in a bit. And let's take a look at the scale option, which is right here. It says scale scales the video output to an integer multiple of 640 by 480. So you remember when we opened the emulator a moment ago, it came up in a tiny little window. Well, probably we want the window to be a little bigger, at least I do. So in my batch file here, you can see I've specified scale number 2, which is going to make it open in a larger window. Now let's take a look at our next option here, which is debug. Now here, if we look for debug on our option list, it is right here. Debug enables the debugger. It's very handy to have the debugger enabled when we're creating assembly language programs, because the debugger, as you will see later in the video, is going to allow us to examine our program in the computer's memory. So that's really handy to have. Now let's take a look at the next option in our batch file here. It says quality nearest. And let's go take a look at that. Quality. Change image scaling algorithm quality. Nearest pixel sampling, linear filtering, best, default, anisotropic, whatever filtering. So I don't know what these things mean. I don't really care what they mean. We're going to actually take a look at this in a moment and try out these different options. What this does essentially is just change the quality of the video when the emulator starts. It changes the way it looks, changes the quality of the characters that appear on the screen, and we'll take a look at that in the moment when we actually play around with this batch file. But that's what the quality option does, is it selects the quality of the image that gets displayed in the emulator. All right, back to our batch file. And the next option here is PRG. So let's find that in our instructions. PRG lets you specify a .prg file that gets loaded after start. So this is allowing the emulator to automatically load the machine code program into memory automatically when we start up the emulator. So this is optional. We don't need to have this specified. So here, if you want, we could just delete this PRG. If you don't want the emulator to automatically open a file when it starts, we don't need this option. We can just delete this completely, and then it won't have any program loaded in its memory when it starts up, which is fine. However, if you do use this batch file to start the emulator, then you may find it handy to have it automatically load a particular file if you always use the same file name that you want to just modify. It's up to you if you want it to automatically load a file for you or not. Here I've just specified the full path to my file. So in this case, it's loading a file called jprog.prg, and it opens a PRG file because that is the file type of the machine code programs we're going to be creating, or rather that the assembler is going to be creating for us. And this is just the path to it. It's on my C drive under a folder called Commander X16, which has another folder called Emulator, and within that folder, that's where my program lives, jprog.prg. But again, like I said, we could just erase this if we don't want it to automatically load a file into memory for us. All right, so now let's try playing around with this batch file and use it to open our emulator. All right, so here I am back in my emulator folder, and here's my runme.bat batch file that we just took a look at, and I'm going to click on it now to open our emulator. And there you go, see, it's opened our emulator, and it opens this black command window as well, and then it opens the actual emulator screen here that you can see. And you can see right now that the window is much larger than it was when we opened it without using that scale parameter. So if I go back to my batch file here, you can see the scale is 2. If I change that to 1 and I save this batch file again, and I'll go back and reopen this emulator by clicking on the runme.bat file again in the folder, and every time you open this emulator, it opens a new instance of it. So the existing emulator window that you may have open on the screen, it just stays there, and it'll just open a second one in addition to it. So let me open a new emulator window now. And you can see now that I changed the scale value to 1, it opens a little tiny window. So I'll go ahead and close this now. And I still have my original emulator window open here. And it's looking pretty good. You can see the text on it is super sharp on this emulator. It's looking really nice. So let's go ahead and change another parameter and see how that affects our display. So let's modify this quality parameter now, and you can see I have it set to nearest. And as we saw on our list of instructions for these options, if I look at the quality option again, you can see the options are nearest, linear, and best. So let's just try each of those and compare them and see what they look like. So right now we have nearest. What if I change that to linear? And I'll save it. And I'll reopen it. Oh, I better change my size back to the big one. Change my scale back to 2. And now I'll reopen it. All right, so this video is now in the linear selection. And if I compare the two side by side here, so you can see this one on the left here, that's the nearest quality selection. And this one to the right of it is the linear quality setting. Now let's try the third option, which is best. So I'll change this linear to best and save it and reopen it. And there, now we have all 3 of these different quality modes shown side by side. So the first one here is nearest, the middle one here is linear, and the third one here is best. So this left one here, which is the nearest quality selection, that's the one I use because it looks the sharpest. And so I'm going to go ahead and close these other windows, and I'll go back to my batch file and change it back to nearest. And save it just like that. So now this debug option here is, as I mentioned before, it allows us to use the debugger in this emulator window. It enables the debugger. So if we don't have that option, then the debugger won't activate when we try to use it. So let's go and take a look at just quickly how we can confirm that's actually working. So I'll go back to the emulator window here. And to activate the debugger, you simply press F12. So pressing F12 will open this window on the right side here, which shows us the different memory locations and the disassembly and the register values. And we're going to be taking a look at this in more detail after we actually create a sample program in assembly language later. But for now, we can see that the debugger is actually active. Our batch file has enabled the debugger option, and it seems to be working. And to get out of debugger mode and go back to the emulator screen, we just press F5, just like that, and we're back in our regular emulator screen. And like I said, we're going to be taking a look at the debugger a little bit more near the end of the video once we have our program created. All right, so there we have our emulator installed, and it looks like it's working. We've set up the different configuration options for it using our batch file here, and all we need to do is save our batch file, and we can run this emulator by clicking on that runme.bat file or whatever you named it on your computer, and that will open our emulator for us. And if you want, we can even specify a file or a program that we want the emulator to automatically load for us. But as I mentioned, we can always leave off this parameter here if we don't want it to automatically load a file for us. We can simply delete that and just leave our batch file just like this. All right, so before we move on, I just want to mention one more way that we can activate this emulator, which is the way we're going to be doing it once we get this development environment configured, is we're going to be activating it from within our editor. So as I mentioned at the beginning, what we're going to be doing is installing an editor that allows us to enter our assembly language program. We're going to be installing an assembler to assemble our program into machine code. And we'll be, of course, using this emulator to run our program. But within our editor, we can also have our Visual Studio Code editor, which is the editor we're going to be using. We can set that up to automatically open our emulator for us. So just as a bit of a recap, there are three ways that we can actually run this emulator. We can run it just by clicking on that exe file that comes installed in the regular Windows package that we installed. It will run the emulator without any options selected. We can run it using a batch file, which allows us to select whatever options we want, which are the ones we've just been playing around with, as well as we can run it automatically from within our Visual Studio Code editor, which we'll see in a moment. All right, so let's go on here to our next step. Now, the next thing we want to install is the retro assembler. So this is the assembler which is going to assemble our assembly language program, which is actually just a text file. It's going to assemble that file into a machine code program for us, which is a PRG file, which our emulator can run. So of course we need an assembler to do that. And let's go ahead and install our retro assembler. And this is actually the name of the assembler we're going to be installing. It's called retro assembler. And I'll put a link to the download page to install this assembler as well in the video description. But let's take a look at it right now. enginedesigns.net/retroassembler. And here it talks about the retro assembler, and it says here the current version is 2022.1, April 29, 2022. And here are the different CPU types it supports. And right here, you can see it's listed the 65CO2, which is what the Commander X16 uses. And here are the output formats it generates after assembling the program. And right here is the PRG file that we're interested in running in our emulator. And so you can read about all the different features of this assembler here. And to install it, I'm going to go here where it says retroassembler.zip. And if you click on that, it'll download the zip file. And you simply, again, unzip those files into a folder of your choosing on your computer. In my case, I've installed it right here under my Commander X16 folder, in this folder here called Retro Assembler. And if I open that, these are all the files and folders that will get installed from that download from the Retro Assembler page. Now, one thing we want to just take note of is if you see up here at the top of this Retro Assembler page, it talks about portable package built for .NET 6. I'm not familiar with really .NET, how it works or what it is, and I'm not sure whether you really need it or not and what it's used for. So I just installed .NET 6 just to be safe. So I'll just show you quickly how I did that. I just went to the website here. If you go down here to how to install .NET on Linux and Mac OS and Windows, I clicked on that and it takes you to this page where there's a link here that says go to the .NET download page. So if you click on that, then that takes you to this page here. And I think I just simply clicked on this link here, .NET SDK X64, and that downloads .NET 6.0. And once that downloads, I just open the folder and install it from there. And this is what the installation window looks like when you go to install this .NET framework. And you just simply click on install and install it on your computer. So again, like I said, I'm not sure if I really needed to install it, but I installed it anyway just to be safe. All right, so let's take a look at our next step now. So we've installed the emulator and we've installed the assembler and we've installed the .NET 6.0 framework. Whether or not we needed it, I'm not sure. And now the last thing to install is the editor, which in this case is going to be Visual Studio Code or VSCode. This is very simple to install. You simply go to the website and download it. And I'll show you that now. All right, so here is the website to download Visual Studio Code. It's code.visualstudio.com. And you simply click on this download for Windows button. Pretty straightforward. You simply download it and install it. All right, so that's the last step on our software installation page. We've installed the emulator, we've installed the assembler, we've installed this .NET 6.0 framework, and we've installed the Visual Studio Code editor. So if you've come this far and you were able to install these three, well, I guess 4 packages, then the next step is to configure these tools to work together to allow us to easily create an assembly language program for the Commander X16. So we're getting closer to doing some fun stuff, and now let's move on to some configuration. All right, so here we are on the configuration page. Now there are several steps to this configuration of these tools, but don't let it seem too intimidating, because I'm the first person to get intimidated by this configuration type stuff. I don't really understand how to do all these configurations on my own. I just simply followed the instructions on the website that we took a look at, that 8-bit coding website. So let's just go back to that website for a moment and see where we're at. All right, so here we are back on the instruction window on the 8bitcoding.com website. And so here it talks about downloading the software. We just completed that step of downloading everything. And if we go down now to the part where it talks about configuring these tools. So we took a look at already configuring the emulator using our batch file, and we set up some parameters such as this quality parameter here. We set it to quality nearest, and our scale, we set it to scale 2. And you can see right here in his instructions, he says for my system, scale 2 and quality nearest works best. And I found that is true for my system as well. So those are the parameters we set up in our batch file. Now let's see what else he has on his page here. Next he talks about the retro assembler. And he says retro assembler has many options we can configure, but let's just focus on the minimum needed and try to explain why we are using them. Sounds good to me. The file we will look at is retroassembler-settings.xml. And if you look at the comment in the beginning, it suggests that we don't edit that file directly. The reason being that with any new update, that file might get overwritten, and therefore our changes will be lost. So we will follow the guidelines and create a new file with our customizations and save them in file named retroassembler-usersettings.xml. And then here you can see the different settings that he's going to suggest that we change. So first let's go back to this paragraph and see what he's talking about here. He says, if you look at the comment in the beginning, it suggests that we don't edit that file directly. So now that we have our Visual Studio Code editor installed, let's go ahead and open it up. All right, so when you open up the Visual Studio Code editor, it will probably show some splash screens like this, and we don't really need to bother with any of this stuff. I'm just going to close this window for now. But the one thing I do want to do here is simply change the folder that we're accessing from within Visual Studio Code. So over on the left here, there's an Explorer. And if you click on Explorer here, this button on the left opens and closes the Explorer window. which shows you what folders and files you have access to. So what I want to do is go up here to File and then Open Folder, and I simply want to select whatever folder I installed the assembler in. So in my case, I want to go to my Commander X16 folder and then select the Retro Assembler folder here. So you can see now the Retro Assembler folder is showing down here because it's highlighted up here, and I'll click Select Folder. And now our Visual Studio Code editor should be showing us the contents of the Retro Assembler folder, or wherever you installed your Retro Assembler program. Then just select that folder to show up on the left here, and now we can see the contents. And it's right here, retroassembler-settings.xml. And if I click on it, these are all the configurations that come pre-installed in this settings file for our assembler. Now, I don't need to concern myself with most of these settings. They look very complicated and confusing, but there are 4 settings that we do need to be interested in, and we'll just go take a look at those on the 8-bit coding website now. So here we are back on our 8-bit coding website. You can see in the instructions it says if we look at the comment in the beginning, it suggests that we don't edit that file directly, and that file that he's talking about is the file that we just opened, which is retroassembler-settings.xml. And if we go back to our file in our Visual Studio Code editor, right here, if we go to the top, you can see there is a note here that says default settings for the Retro Assembler. Best practice is leaving these values intact, especially because updates of the assembler come with an updated settings file, which may cause losing your customized settings. So what that means is if we edit this file, if we ever update this program, this utility, then it's probably going to download another file called retroassembler-settings.xml, and so it's going to erase all of the customizations that we're about to do right now. So it says here, duplicate this file as retroassembler-usersettings.xml and place it into the same directory where the assembler is. The contents of that file will also be loaded and it will not get overwritten by updates. Just keep the modified settings lines in there and it will work fine. So what we're going to do is we're going to modify this retroassembler-settings XML file, and then we're going to save it again as retroassembler-usersettings.xml. Pretty simple. So let's go ahead and see which settings we need to change out of all of these dozens or hundreds of different settings. Luckily, we only need to be interested in 4 of them. So let's go back to the 8-bit coding website and take a look. All right, so here it says custom settings for Retro Assembler to use with Commander X16 Emulator, which is perfect. That's exactly what we want. And so here are the 4 settings we want to change. This one called CPU type, this one called output file type, this one called after build, and this one called launch command. So we're going to go through these one by one and see what they do and why we need to change them. And if I go back to my checklist, just to make sure we know where we're at in our procedure here. So we've finished configuring the emulator, which we took a look at with that batch file, and now we're on to the Retro Assembler. And these are the 4 things we want to change: CPU type, output file type, after build, launch command, as well as there's one final note here that we're going to take a look at in a moment as well. So now we're going to take a look at these different settings that we need to change in that configuration file in Visual Studio Code. So here we are back on his site, and it says the first thing we need to change is CPU type, and we want to change it to 65C02, which makes sense because the CPU inside the Commander X16 is a 65C02. So let's go to our file back in our Visual Studio Code editor, and we want to change CPU type to 65C02. So here we are, we'll look for CPU type here, which is the first one right here. It says CPU type equals string, value is 65C02. So if this doesn't say 65C02 on your configuration file, then just simply type in 65C02 in between these quotation marks. And that's the first step done. All right, the next thing we need to change, it says output file type. And so this assembly program, this assembler, is going to create an output file. Once it assembles our assembly language program, it's going to convert it into a machine code program, and it's going to save it as a file type which we want that file type to be a PRG file because that's what our emulator is going to run. So we simply type in PRG where it says output file type. So output file type is right here. This one, it says output format type equals string value equals PRG. So this output format, we just simply type in PRG here in between the quotes on the end, and step number 2 is now complete. All right, let's take a look at step number 3, the third configuration we need to change. It says after build value equals copy.bat. So let's explain this one a bit. Well, actually, let's read his description of this first. And you can see, if you want to follow along with his instructions on the website, you can scroll down and he actually has descriptions outlining what the reasons are for changing these different selections. So here's the CPU type, we changed it to 6502. The output file type, we changed that to PRG because we're going to be loading a PRG file into our emulator. And then here it says after build. It says here we can define a command that will be called after compiler successfully builds the program. We will use this to start a very simple script to copy the finished program into the emulator directory. In my case, the copy.bat program contains only one line, and that's his line right there. So what we're doing here is we can have the assembler automatically run a program for us, or a batch file, once it completes assembling our text file into a machine code program. So our assembly language program is going to be typed into Visual Studio Code. We're going to run the assembler to assemble it into machine code. But then after that is done, we can also tell it to run another program for us if we want. In this case, he's having it run a program called copy.bat, which is a batch file, to copy the output program from one place to another. So you don't need to do this if you don't want to. It's just a convenience. If we take a look at my configuration line in Visual Studio Code, and before we take a look at my file, I'm just going to show you how we need to save this, because remember it said we need to save it using a file named retroassembler-usersettings.xml, which I've already saved my file, of course, under this name, but of course you need to save your file under this name as well. So once you finish making your changes that we're talking about right now, you simply go up to File here, Save As, and then you would specify a file name called retroassembler-usersettings.xml. So what we're going to do now is just open my file that I previously created using that name, which is right here, retroassembler-usersettings.xml. And we can see the changes that I made to my file. So first up here, you can see I've already changed the CPU type to 65C02. I changed the output format to value equals PRG because I want this assembler to output a PRG file. And now the next thing we need to look at is this after build setting right here. And the value is copy.bat. So that means after the assembler finishes assembling my assembly language program, it's also going to do one more thing, which is it's going to execute this file called copy.bat. So what I've done is create another batch file which simply copies my output program to a different folder. Now again, you don't need to do this. You can if you like. So what is going to happen here is once the assembler assembles my program, it's also going to copy that output file, the machine code program, to a different folder. So let's take a look at my copy.bat batch file, which is right here, copy.bat. And here it is. It's a simple one-line instruction. It says copy jprog.prg. So this is the output file that this assembler is going to create for me. And it's going to select this name because that's the name that I'm going to save my assembly language program as. So it's going to create an output file that uses the same name as whatever you save your assembly language program as we'll see a bit later. So here it's going to create this output file called jprog.prg once it does the assembly process, and then it's going to execute this copy.bat file where it simply copies this output file jprog.prg, and it's going to copy it to this folder here, C Commander X16 Emulator and jprog.prg. So it's simply going to copy the output file from the assembler folder over here into the emulator folder, just in case I want to run that program manually from within the emulator folder. So if you want, you can set up a file called copy.batch in case you want your assembler to automatically execute a batch file for you as well. All right, so now let's go back to our user settings file and we'll take a look at the last parameter we need to change. So back here on the 8-bit coding website, the last parameter is called launch command. And then there's a big string here of what we need to type into that field. And the string here should look familiar to you because it has a lot of the same parameters we just looked at to launch our emulator. And that's exactly what it does. It launches our emulator using this string, which is almost the same string that we put into our batch file. So if we take a look at my configuration file in Visual Studio Code, right here, you can see my launch command is specified with this instruction here. And it simply shows the path to where the emulator is stored, which is right here on my C drive under the Commander X16 folder. And underneath that, there's another folder called Emulator. Underneath that, there's a file called X16 emu.exe. And here we have all the parameters that we discussed previously that I want the emulator to use when it opens. And then the last thing here we have is the -prg option, which we discussed earlier, specifies which file we want our emulator to automatically load when it opens. And here we just have a 0 surrounded by these curly braces. So that means it's going to automatically load the machine code program that this assembler creates into our emulator when it opens automatically. So whatever string that you put into your batch file to open your emulator, this is what you would type in here, except you want to put probably the full path here with your hard drive name and all the subfolders as well, just to give it a complete path to this emulator execution file. And now let's go back to our instruction page right here, and you can see that is the last instruction that we need to change, or the last setting we need to change. However, there is another note at the bottom here which says it is important to mention one setting that we didn't change because it is affecting the behavior. Launch enabled stayed set to false in the default setting. Reason for it is this way we have an option to either just build and copy assembly program or build and start it from the editor. This is done by overriding the setting inside of Visual Studio Code keyboard shortcut setting. So what we're going to do is just simply make sure that this launch setting is set to false. So back in my configuration file here, I'll look for the launch setting, which is right here. Launch. Type equals Boolean, value equals false. Okay, so let's go back to my checklist now and see where we're at. All right, so again, we finished configuring the emulator, but now since we've configured our Visual Studio Code editor to launch our emulator for us, we don't actually need to use this batch file that we were playing around with before to open our emulator if we don't want to, because we can have our Visual Studio Code editor automatically open our emulator for us, or rather the assembler is going to open it for us because we just typed in that command into our Visual Studio Code configuration file, or rather the assembler configuration file. So step number 2 here, we were just doing retro assembler configuration. These are the changes we made to that configuration file. We changed the CPU type to 65C02. We changed the output file to PRG. We specified an after build file to execute automatically, which is this copy.bat batch file, which is going to copy our output program from our assembler folder over to our emulator folder. And then we specified our launch command right here with these parameters that will actually open up our emulator for us using these different options. And we confirmed that this launch setting was set to false. So there's only one more thing we need to configure now, which is the actual Visual Studio Code editor. And what we want to do with the editor itself is we want to, first of all, install an extension, which is going to give us syntax highlighting for when we type in our assembly language program. We want the editor to recognize that we are actually typing in a 65C02 assembly language program, and it will give us some nice syntax highlighting for that and change the color of the different text when we enter our program, as well as we can set up some hotkeys here, which will allow us to automatically either assemble our program for us by itself, or it will assemble and load the program into the emulator for us. So what we want to do is, first of all, let's go ahead and install our RetroAssembler extension. All right, so here we are back in the Visual Studio Code editor, and I can go ahead and close this file now, this retroassembler-usersettings.xml file. Just make sure that it's saved. So just go up to File and make sure that you save this new configuration file as retroassembler-usersettings.xml, and you want to save it in the same folder where you installed the RetroAssembler itself. Now I can close this. So what we want to do is install an extension to give us syntax highlighting for RetroAssembler programs. And that's very easy to do. All we do is go over here to this selection here that allows us to find extensions, and we click on that. And of course I've already installed this extension into the editor, but I can search for it here. I'll type in RetroAssembler, and here it is right here, RetroAssembler. So if I click on this, it gives you a description. It says assembly language extension for RetroAssembler using whatever, and here's our 65CO2 right here we're interested in. So this one is already installed, and if you want to install that, you would have a button here that says install. Mine says uninstall because I've already installed it, of course. So you simply install this RetroAssembler extension, and it will give you syntax highlighting for your assembly language program. So that's pretty simple. I can close that and go back to our instructions now. All right, so let's read the instructions that are shown on this 8-bit coding website again. And it says Visual Studio Code. The final step is to configure the Visual Studio Code. Luckily for us, that is mostly pre-configured already. Just go to the settings and open the extensions search. So I just showed you how to install the extension for RetroAssembler, so we don't need to go through this part because we just installed that. But the next part we can do, which is right here, it says the last thing remaining is to set up the shortcuts to compile and start the program. Again, the settings can easily be found under File menu. So here it shows you under the File menu, it shows Preferences and Keyboard Shortcuts. And so let's go and find that. So here we'll go to File and then Preferences and Keyboard Shortcuts. And you can see there's already a ton of keyboard shortcuts already configured by default in this Visual Studio Code editor. So in this case, let's say you want to use the F4 and F5 keys, which is what I used and which is what is shown on the 8-bit coding website. You can use whatever key combination you like, of course, but since I'm using the F4 and F5 keys, first what I'm going to do is search for F4 in the search bar here, and we're going to see if there are any commands already assigned to that key. And you can see right here there's only one instruction or command that's assigned to this F4 key by itself, which is the one that I've already configured for our RetroAssembler. And similarly, if I search for F5, you can see that there's only one selection here that has only F5 selected by itself, which is RetroAssembler build and start. And so how would you change this in your Visual Studio Code editor? Well, it's very simple. You simply search for whatever keys that you want to assign. So I'll just redo mine and show you how it's done. So again, I'll search for F4. So let's assume this F4 key was originally assigned to something else. So I'm just going to press the delete key on my keyboard to erase this assignment. Just like that, and now it's gone. So now there's nothing assigned to the F4 key. And now I'm going to go up here to my search bar again and search for RetroAssembler. And right here, you can see it shows me 4 different options for RetroAssembler. And in this case, I want RetroAssembler build. So I'll go ahead and click on that. And I'll click plus. And it says press desired key combination, then press enter. And you can select your own key combination. In my case, I'm just going to simply select the F4 key by itself, just like that. And now I'll press enter. And there we go. So now I have the F4 key assigned to automatically build, which is assemble our program in the retro assembler. So now when I create my assembly language program and I want to simply assemble it without loading it into the emulator, I could press F4. And I would do that, for example, if I just wanted to see if it assembles correctly without any errors, for example, without actually running it. But now let's go ahead and do F5. So if I search for F5 here, you can see F5 is already assigned to retro assembler build and start. So I'll highlight that and I'll delete it. And now I'll search for retro assembler again. And I'll reassign it just as if I'm pretending that it wasn't already assigned because I just deleted it. So here we have a selection here, retro assembler build and start. So that's the one that I want. I click the pencil to edit it and I'll press F5 and enter. And there, so now we have F5 assigned to retro assembler build and start. And you can see here that retro assembler build is now assigned to F4, retro assembler build and start is now assigned to F5. So now when we type in our program, we can press F4 to assemble the program into machine code, or we can press F5 to assemble the program into machine code and automatically open our emulator and load this program into our emulator. So it's going to be a very smooth and cool and fun development process now for creating assembly language programs for the Commander X16, which is exactly what we're going to do next. Alright, so hopefully you were able to follow along with all of those steps and it wasn't too painful. But the good news is the hard part is done now. And now that we have all these tools installed and configured on our computer, we get to do something a little more enjoyable, which is actually creating an assembly language program that we can run on the Commander X16 emulator, or if and when we're lucky enough to have an actual Commander X16 computer, we can run it on that. So before I start creating our first assembly language program and describing some of the different aspects of the process that we need to be aware of, I just wanted to share with you a really cool book that I found that is probably not very well known because, well, I didn't know about it before I happened to run across it on Amazon. And me having never actually done any programming on a Commodore computer before, I actually surprisingly never owned a Commodore 64 or a VIC-20 or any Commodore. Well, actually I did own an Amiga 500, but I never did any programming on it. Although I would have loved to have a Commodore 64, and that still is pretty much my ideal goal computer to have at some point, but I think I'll settle for a Commander X16 instead. But anyway, I just want to share this book with you because at least I found it from a perspective of someone who's never done any programming on a Commodore before and not really having any familiarity with Commodore computers. I found it to be a very interesting book that was well written in a style that I enjoy reading, and it covers different aspects of the Commodore computers. It's not designed for the Commander X16 computer, but I just wanted to share it with you in case maybe you're not familiar with Commodore computers. It talks about programming in BASIC on regular Commodore computers like a Commodore 64, and it even talks about creating graphics and sound, and also it gets into machine code. And it's a really good book. I just want to quickly share it with you now, and I'll put up a screenshot of it here somewhere. And it's called Start Here, The Fundamentals of Commodore 64 Programming in BASIC and 6502 Assembly Language for Real or Emulated C64s. And it even covers the C64 emulator. And actually, why don't I just get the actual book for you and I can do a quick flip through it for you. All right, so here is the book here. John McInnes, Start Here, The Fundamentals of Commodore 64 Programming in BASIC and 6502 Assembly Language for Real or Emulated C64s. So if we take a look at the back here, it says, this book was written with the beginner in mind. However, it isn't light on information. This book includes such essential Commodore 64 topics as Commodore Basic V2, which if you're interested in programming in BASIC for the Commander X16 and you're maybe not familiar with Commodore Basic version 2, then this book does cover that as well. Although if you're going to be doing any type of peeks or pokes, the Commander X16 does have different ROM routines and different addresses for the ports and stuff. So although the basic programs I believe should work on the Commander X16, anything using machine code or peeks and pokes or ROM routines probably won't work if you're translating them from the Commodore 64 to the Commander X16. But this book is very interesting for me, again, like I said, as a newbie to the Commodore world. And if I just flip through it here, you can see that it does have some screenshots, actually a lot of screenshots. It describes how the programs work, and it shows you the output of the programs, as well as it shows you the program listings. And I just found it to be a really interesting book, and it even has the actual colors I guess would be on a C64 screen. So anyway, I just wanted to quickly share that with you in case anyone is interested in it and you're considering maybe checking it out. If you are a beginner to the Commodore world and you're interested in learning about programming on the original Commodore 64, maybe check it out. I'm not affiliated with this book in any way. I don't know the author or anything. I'm not getting any affiliate link money from this thing or anything. I just happened to find the book on Amazon and I really enjoyed reading it, and so I just wanted to share that with you. Okay, so now that we've got these tools installed and configured on our computer, let's go ahead and write our first assembly language program for the Commander X16. So there are some points that we need to be aware of when we're going to create an assembly language program for the Commander X16. And some of these are probably similar to creating a program for the Commodore 64. I'm not sure, but these are points we will need to be aware of when creating an assembly language program and a machine code program for running on the Commander X16 or the Commander X16 Emulator. And let's just go through them one by one. So the top one here says execute our machine code program from BASIC using run or sys. And of course we're going to go through these hands-on and do some exercises and play around with these things. But what this first point means is once we assemble our program, or we assemble our assembly language file into a machine code program, we want to run it on the emulator from BASIC. So when the emulator starts up, it's running in BASIC. The BASIC interpreter is running. So in order to execute our machine code program, we need to load that program into memory, into the emulator, and then execute it. And the way we're going to do that is from BASIC using either a run command here or the sys command. And we're going to take a look at both of those instructions in a moment when we actually look at this in real time. Okay, the next point here says the BASIC interpreter expects the BASIC program to start at 0801 or 2049 decimal. So this is going to become important to us when we're actually creating our assembly language program, and we can refer back to these notes when we do that. But what that means is when we create our assembly language program, if you're familiar with assembly language, you can tell the assembler where in memory you want it to assemble those machine code bytes and store them in memory at a particular location. So when we're running our program from BASIC, it says here that the BASIC interpreter, which is what runs automatically when we start the emulator or the computer itself, it expects the BASIC program to start at 0801. So we're going to have, as you'll see in a moment, our assembly language program start at address 0801 as well. However, there are a couple of more points we need to be aware of, such as point number 3 here, which says machine code bytes basic header start at 0801 and program starts at 080D, which is 2061 decimal. So these numbers may or may not mean anything to you right now, but they're going to mean something to you in a moment once we get into our program. But what that means is when we create our assembly language program, we're going to inject some extra bytes of code at the beginning of the program before our actual assembly language program that we want to run to do stuff, right? So, and those extra bytes are going to be a basic header because the computer expects there to be a basic header at the beginning of our code in order to be able to run our program from basic. And this will all become clear in a moment when we actually do it. The fourth point here says our assembly program will create a tokenized basic header. So these extra bytes that I just mentioned that we're going to be putting into our assembly language program or our machine code program, these are actually going to be a tokenized basic header, and we're going to look at that in detail. And then finally here it says executing the machine code program. We can do that in two different ways. First, we need to load our program into memory using this load instruction here, load myprog.prg, assuming your program is called myprog, or it could be called whatever you save your program is. Obviously, you would load it into the emulator using this load instruction here. So that will load our machine code program into memory, but then we need to execute our machine code program, which we will do either by using the run command or the sys2061 command. So this is just kind of a preview as to the information we'll need to be familiar with and keep in mind when we're creating our assembly language program. But like I said, we can refer back to this as we're making our program. So let's go ahead and take a look at our assembly language program now. All right, so here we are back in our Visual Studio Code editor. And if you were to create an assembly language program from scratch, designed for the 65C02 processor, the way you would do it is simply go to File, New Text File, and then it asks you what language do you want to create your program in. And so if I click on that, select a language, I'm going to search for Retro Assembler right here, and you can see it has all these different Retro Assembler options, and of course I want this one here, Retro Assembler 65C02. And now when I type in my program, it will have syntax highlighting for 65C02 assembly language. So for example, I could type LDA 01. The highlighting is not super obvious in this particular example. My opcode here is in dark blue and my operand is in light purple, it looks like. But anyway, it does give us syntax highlighting. And if you wanted to, you could change the theme of the editor by going here to File, and then down here to Preferences, Theme, and you choose Color Theme. And there are all these different colors you can choose from if you want to change the look of the assembler. So for example, here's one called Retro Assembler. Let's see what that looks like. Oh, that's pretty bright. Maybe I'll try Retro Assembler Blue here, which looks like this. So you can choose whatever color theme you like. And this is Retro Assembler Blue, for example. But now let's go ahead and open the sample template program that I created already. And I've saved it using this file name here, jprog.asm. So here it is here. Here's my program, jprog.asm. This is my assembly language program that I created. And it's really just a very simple template to begin our program just to get something working. So let's go through it now and we'll see what it does. So the first line here is an org instruction. And by the way, if you're interested in finding out how to use the assembler, there is a document we can take a look at. So let's go to our assembler folder where we installed our retro assembler, which is right here. And you can see under the retro assembler folder, there's another folder called documentation. So if we open that, you can see there's a file called retroassembler.html. So let's go ahead and open that. And here it gives you all kinds of information on how to use this retro assembler. For example, here are directives, and these are all the different directives it can use. For example, the org directive in my program is right here. And if you click on it, it says instructions and data bytes are always placed in the currently selected memory segment. So I can use the org instruction to tell the assembler where in memory I want my machine code bytes to be stored. And that's what I'm doing in my program. Right here, you can see I've used the org assembler directive .org, and I've given it an instruction value of 0801 hexadecimal. So then it's going to store our program or our machine code bytes into memory beginning at address 0801. And if we go back to my notes here, you can see that our point number 2 says the basic interpreter expects the basic program to start at 0801. Now you might be thinking, well, what do we care about a basic program? We're creating an assembly language program that's going to be converted into machine code, which is true, but our basic interpreter, which is essentially our emulator, it expects a basic program to start at 0801. So we're going to have our assembly language program be stored in memory at 0801 instead, and we'll see why in a moment. And if we just go back to this documentation again, you can go through it and see all of the different instructions on how to use this assembler. And if you click on instructions here for the 65C02 family of processors, it shows you the different instructions that you can use, as well as you can look up the different value types for numbers and strings and characters and labels. Or if you want to run this assembler separately manually without going through Visual Studio Code, or if you want to run it using some options, here are some options that you can select. -C turns on case sensitive mode for labels, functions, and macros, for example. So there are different options you can use if you want to. So this is the documentation for the assembler. If you are interested in learning more about it, you can just go through this documentation and read about it. All right, so back to our program here. So this org instruction tells our assembler to convert our assembly language program into machine code and save it in memory beginning at address 0801. So remember, our note just said that the basic interpreter expects a basic program to be stored at address 0801. So instead of having a basic program, we're going to put this header into our assembly language program, which stores some bytes. And if we take a look at my instructions again, point number 3 here says machine code bytes basic header start at 0801. Program starts at 080D, which means we're going to create a basic header at 0801, and then our actual machine code program is going to start at 080D. So let's see what that looks like. So here at 0801, we're going to have some bytes stored in memory, which we do by using this .byte assembler directive, which stores bytes of code in memory. In this case, it's just byte of data. Actually, it's not bytes of code. So these are the bytes that we're going to be storing in memory at 0801. So what we're trying to do here, and you'll see this in a moment when we actually take a look at this in the emulator, is we're going to create a tokenized basic, program, a one-line program, which is going to be injected into the emulator when we run it. And these are the tokens here, or the values that represent the tokens. So if you're not familiar with tokens, tokens are like, for example, when you enter a basic instruction in a basic program you're creating, well, the computer doesn't save the word for and the word next and the word print and all those things. Instead, it saves tokens of them, or shortened versions of those instructions, so it takes up less room in memory. And so these are the bytes here, 0B, 08, 0A, 01, and so forth, that we're saving in memory at the beginning of our assembly language program, or actually at the beginning of our machine code program. And let's see what these bytes represent. So here is the description of what these bytes represent here. Okay, so this is our basic header, our tokenized basic header, and this is what the bytes mean. So these two bytes here, 0B, 08, they represent an address where the basic program would normally begin. So we're not entering a basic program, we're entering a machine code program, but this is the address, I think, where it would normally expect the basic program to start. And this is written in a way, or stored in memory, in a format that's called little endian. So these two bytes here, 0B and 08, would represent an address of 080B. And we can see where 08OB would be here from our string of data that we're storing into memory. Since our org instruction specifies the starting location of 0801, that means that this first byte, 0B, is going to be stored in memory at location 0801. So if we want to find location 08OB, then we can just count from the beginning. So this is 0801, 0802, 0803, 4, 5, 6, 7, 8, 9, 080A, 080B. So this second 0 value here would be located at address 080B. And this is what this address here represents. So if we had a basic program, I think this address means that's where it would look for that basic program. So that's what these two first bytes represent, I think. And so let's take a look at the next two bytes here, which are 0A and 01. What do they mean? Well, it says right here, 0A01 equals little endian. That's what I just mentioned, little endian, where the low byte is stored before the high byte. It says little endian for 010A, which is 266 in decimal. It says that this value, 010A, or 266 in decimal, it says arbitrary line number for the sys command below. And we're going to see that in a moment when we run this program. So let's go on to the next byte here, which is 9E. It says 9E equals sys command in basic. So here you can see we're actually creating a line of a basic program that starts at line number 266, and it uses the instruction sys. And the next bytes here, after 9E, we have 32, 30, 36, and 31, which you can see here says 32, 30, 36, and 31. These represent the PETSCI codes for the digits 2061, which it says here, PETSCI coded, needed for the sys2061 basic command to run the machine code program. So when we run our machine code program, we can use the instruction sys2061, as we'll see in a moment. And so these bytes of code make up the rest of our basic instruction line, sys2061. And then after that, we just have 3 zeros here, which are just used for padding to give us enough bytes so that our next instruction, which is our actual assembly language program or machine code program, which starts down here. So these instructions are going to get converted into machine code bytes, and they are going to be stored in memory at 080D, which it says right here. The machine code bytes below will begin at address 080D. And we can confirm that by looking up here. So 0B starts at address 0801. So that's 0801, 2, 3, 4, 5, 6, 7, 8, 9, 080A, 080B, 080C. So this last padding 0 here will be stored in memory at address 080C, which means the next byte of data will be at address 080D, which will be down here where our actual assembly language instructions get converted into machine code bytes. Okay, so that might all seem kind of confusing, but let's run it in our emulator now, and we can play around with it and actually get comfortable with what this means. And just in case you're not clear about these 2061 values, let me just bring up a PETSCI code chart, which is right here. And if I scroll down to the numbers, and I'm looking for numbers 2061, so right here, for example, here's 2, which has a code of 32, 0 has a code of 30, 6 has a code of 36, and 1 has a code of 31. So 2061 would have codes of 32, 30, 36, and 31. So back in my program, here they are right here, 32, 30, 36, and 31. So these hexadecimal bytes represent the PETSCI codes for the digits 2061. So now let's take a look at our actual assembly language program. And it's a very simple program. It only has 3 instructions. The first one says LDA, or load A, $A6, or actually hashtag $A6. And what this does, as it says here in the note, is it says load register A with PETSCI code for checkerboard symbol. So let's go ahead and take a look at that PETSCI chart again. And if we look right here, you can see this code A6 in hexadecimal corresponds to this checkerboard symbol. So the checkerboard has a value of A6, and back in our program, that's the value that we're loading into the A register, A6 right here. So we're loading the value of A6 into the A register, and that A6 represents the Petsky symbol for that checkerboard character. So our next line here says JSR FFD2. So JSR represents the jump subroutine command. So it's like a call instruction. It's going to execute a ROM routine located at address FFD2. So what ROM routine is actually located at FFD2? So to get the answer to that, let's take a look at the Commander X16 documentation, where it talks about the different ROM routines that are stored in the kernel. All right, and here we are in my emulator folder where I have this emulator installed. And let's open up this docs folder. And we want to find out what ROM routines are stored in the kernel. The kernel is the program that operates the computer when it is turned on, right? So let's open up this file here, kernal.html. And we'll look for this address here, FFD2, and see what the subroutine at that address actually does. So here's the chapter here on the kernel. And if I go down here and I look for that address FFD2, here's the address right here, FFD2. It says BS out write character. And if I look on the GitHub page right here, you can see it lists the kernel API functions as well. And if I find FFD2, it's right here, FFD2, and here it's called char out, which I guess stands for character out. And it says alias for BS out. So it's the same address, FFD2. Here it's called char out. I guess the Commander X16 calls it char out, and the Commodore 64, maybe they referred to it as BS out, which it says here, BS out. And it says write character. So essentially what we're doing is we want to call a ROM routine which is going to output a character to the screen. And the character that is going to output is whatever character is stored in the A register. So back in our program here at line 13, we're storing a value of A6 into the A register. And this A6 represents that checkerboard pattern. And then in line 14 here, we're going to call a ROM routine at address FFD2, which is called char out, which will output whatever character value is stored in the A register to the screen. And then finally our last line at line 15 here is simply a return command which returns control of the computer back to basic. So now if we try assembling this program using that hotkey that I set up, which is F4, remember? So I'll go ahead and press F4 now and assemble the program. So there to assemble the program, it says pre-processing the source code file, 5 lines of code loaded, compiling first pass, compiling second pass. And the reason it goes through 2 different passes, I think, is because sometimes it might not know what values are assigned to different labels. So once it goes through the program the first time and it completes its first pass, then it has an idea of what values are assigned to some of the labels, and it can go back and do the second pass and finalize assigning values for the rest of the labels. Success, size 18 bytes. There's no errors being shown here. So now we should have an output file called jprog.prg in our assembler folder. And if we take a look here, here it is right here, jprog.prg. So that's the assembled program, which is a machine code program we can load into our emulator. So let's try doing that manually now. And remember, we had our copy.bat file here that gets executed automatically as well once our program is assembled. And if we open that and take a look at what that does, our copy.bat file copies our jprog.prg file over into our emulator folder so that I can easily access it from within the emulator. So let's go and open our emulator now manually. All right, so here I am in my emulator folder, and I should have that jprog.prg file saved in here now as well, because our assembler copied it over here using that copy.bat batch file, remember? So let's look for it here. It's right at the top here, jprog.prg. Here is a copy of our machine code program in our emulator folder as well. So it exists in 2 places now. It's in our assembler folder as well as in our emulator folder. So now let's go ahead and manually open our emulator by clicking on this runme.bat file. But before I do that, let's take a look at it one more time. So here's our batch file, And remember at the end here, we had this option to automatically load a program into it when we open the emulator right here. It says PRG, and then it has a path to this program called jprog.prg. So here's our machine code program file here. And if I execute this batch file now, it's going to open the assembler and also automatically load in this program into memory. So let's try opening this emulator first without it automatically loading this program into the memory. So I'm just going to delete this last part here and save it. And now when I click on this runme.bat, it should open the emulator without loading any program into memory. So there we go, we have our emulator loaded. And if I type list, you can see there's nothing in memory. There's no basic program in memory. And if I want to load that program now manually, I simply type load jprog.prg and enter. And now it says it's loaded it. And you can see here it says loading from 0801 to 0813. So it does load our bytes into memory beginning at 0801. And now if I type list, you can see there's a basic program in here, line 266, sys 2061. So let's take a look at this in more detail. But before we do that, let's go back and modify our batch file to automatically load this program so we don't have to type load jprog.prg. So let me close this emulator now, and I'll go back to my batch file. And now I'll repaste in my previous text, which will automatically load my program into memory, jprog.prg. So now I shouldn't have to type load jprog.prg manually anymore when I open the emulator. So I'll save this, and now I'll run this batch file. Here I'll click on runme.bat again. And now you can see when it opens the emulator, it automatically loads my program into the emulator for me, because remember I copied my program into this emulator folder. So here it says loading from 0801 to 0813. So my program should be loaded into memory. And if I type list now, you can see there's my program. It automatically loaded it into memory for me. So now let's take a look at this program in detail and see what it's actually doing. So this basic line here, 266 sys 2061, is the basic instruction that's going to execute our machine code program. But before we run our machine code program, let's take a look at how this basic program actually got here. So back in our Visual Studio Code, now we should be able to understand what these bytes mean here. As I described before, these bytes are actually a tokenized basic program line, and it contains exactly what we covered earlier. It first has this little endian value. This actually isn't an address, but it's a value, and this value represents a line number. So our basic program that you just saw that was loaded into our emulator, right here, you can see it has line number 266. Well, this is where the line number comes from right here. So these third and fourth bytes, OA01, they convert into a value in little endian format of 010A, which represents 266 in decimal. And it says here arbitrary line number for the sys command below. So our basic program has a line number of 266. And we can change that if we want right here. If we maybe change this value from 010A. So 010A is going to be 01 multiplied by 256 because it's the high byte, plus A, which represents 10. So 01, 256, plus 10 is 266. So if we change this 01 to 00, for example, and then we reassemble it, I'll press F4 now. Okay, so now it's reassembled. So now I would expect our basic program to have a line number of just 10 because we erased that 01 from the high byte. So let's go ahead and reload our program into the emulator now. And now if I manually reload it, load jprog.prg and press enter, it says it reloaded it successfully. Now if I do a listing, let's see what line number we get. Oh, we get the same value of 266. And can anyone guess why we have the same value of 266? So after you stop laughing, then I'll explain why that is, because, and I've done this before in previous videos, because I changed the value in my note here to 00, but I need to actually change the real value that we're storing in memory, which is up here, 0A01. So this 1 here is the one I need to change to 00, not just the comment. So now if I change this value to 00, then the high byte should be 0, the low byte should be A, which has a value of 10 decimal. Now I'll reassemble it by pressing F4. Okay, and it should be done. Now let's go back and reload it again. Load jprog.prg. And now if we list it, let's see if our line number is any different. There we go. Now our line number is changed to 10. So now we can easily change that line number. So now instead of 000A, maybe we change that to 00FF. Well, actually it's FF00 because the low byte comes first. So if I change this to FF now and I reassemble it, and now it's done, and of course FF should have a value of 255. And if I go back to my emulator now and I reload the program, there it is. Now I would expect it to have a line number of 255. And there it does. So we've just confirmed that that's what those 2 bytes in our program do. They determine the line number of the basic program that shows up in our emulator. So now let's take a look at the other bytes. And the next byte here is 9E, which here it says 9E represents the basic command sys. And we can easily confirm that in our emulator by taking a look at our output from our listing here. It says 255, line number 255, sys 2061. So that matches up with our program here, where 9E, this byte here, represents the basic instruction sys, and then the following bytes, 32, 30, 36, 31, represent the PETSCII codes for these characters 2061. And we could confirm that by changing one of them. Let's say instead of 2061, we change it to 2062. So we could change this last 31 code here to 32 and reassemble it. And now our basic program should say sys 2062 instead of 2061. So we'll reload it now. And we'll list it again. And now it says line number 255, sys 2062. However, we want that to stay at 2061, so I'll just change it back now to 2061. And the reason we want it at 2061 is because our assembly language program begins at address 2061 decimal, which is 080D in hexadecimal, as you can see here. 2061 decimal equals 080D. And we can just confirm that if we want to by going to our calculator. We'll go into decimal mode, clear it, 2061. You can see here 2061 decimals equals 80D or 080D, which is what is in our program here, 080D. So our actual assembly language program now begins in memory at address 080D, and we can confirm that by using the debugger. And let me see, I have a slide about the debugger as well right here. So now that we've gone through our assembly language program and that basic tokenized header that gets injected into our program manually, we can take a look at the debugger and play around with the debugger a little bit. So first of all, it says readme.html in emulator docs. So let's go to the emulator folder and look for readme.html. So here we are in the emulator folder. Here's the docs folder. So I'll open that. And here is readme.html right here. Let's open that. And this gives us information about how to use the debugger. So we can go down to the debugger section here. And this gives us actually information about using the emulator, but the debugger is part of the emulator. So I'm just going to go down and find the debugger section right here. So debugger. So the debugger requires -debug to start. So remember that's why we put this debug option in our batch file to manually start our emulator, and we also put this in our configuration file in Visual Studio Code for our assembler. So this debug option allows the debugger to operate within the emulator. And here are some instructions here that we can use in the debugger. So D, for example, does a disassembly listing, M does a memory dump, V displays VRAM, and then B changes the memory bank, and R changes the register value. And we can see that in my notes as well. Right here, I've just made a summary of some of the more important keyboard commands we can use in the debugger. F12 opens the debugger. F5 returns from the debugger back to the emulator basic interpreter screen. D disassembles from a certain address. M does a memory dump from a certain address. V displays the VRAM contents. So the VRAM is video RAM. So this computer has a Vera board which controls the video. It has its own RAM memory installed, which controls what gets displayed on the screen. So if you want to see the contents of the video RAM, then you can use this V command in the debugger as well. And then here we have a R, which changes the register value, and then page up and page down on the keyboard will scroll up and down on the output. So let's give some of these, or maybe all of these, a try. All right, so here we are back in our emulator, and let's go ahead and press F12 to activate our debugger. And there it is. There we have our debugger. And if we want to try out some of those commands, let's go ahead and do that. So the first thing we can do is let's do a memory dump at the address where our program should be stored. So back in our program listing here, you can see that we did an org 0801. So that means these bytes here, 0B, 08, FF, should be stored in memory starting at 0801. So let's go and do a memory dump of address 0801 and look for these bytes, 0B, 08, FF. So if I type M for memory dump and then space 0801, you can see that our output changes to show us the contents of these memory locations beginning at address 0801. And you can see indeed we do have 0B, 08, FF, which is exactly what we would expect from our program right here, 0B, 08, FF. And as we described before, our actual assembly language program, the bytes for that should begin at address 080D. So let's do a disassembly now of address 080D and see if our program shows up there. So now I'll type D for disassembly, then space 080D and press enter. And now you can see at the top of our window here, we have a disassembly listing of our assembly language program beginning at address 080D. And here are the instructions here. Load A6, jump subroutine FFD2 and return, which should correspond to our program. Load A6, jump subroutine FFD2, and then a return. So that's pretty cool. We can see a disassembly of our program right in this debugger here. And we can try some different commands here. If we wanted to, for example, examine the video memory, we could type V space, maybe, I don't know, 1000. I don't know what the video memory addresses are, but if you want to view the video memory contents, you can use the V. And there's the contents of the video RAM. If you want to change the contents of one of the registers that are shown up here, so you can see, for example, up here we have the A register has a value of 01. What if we want to change that? Well, we can simply type R for register and then space, and then A, which is the register we want to change, and then space, and maybe we'll give it a value of FF. So I'll type FF and then press enter. And now you can see our A register contains a value of FF. So the debugger is pretty cool. And then if we want to return back to our regular emulator screen, we simply press F5, just like that, and we're back in our regular emulator. So now let's go ahead and run our machine code program, which we now have just confirmed is actually stored in memory beginning at address 080D. which corresponds to decimal address 2061. So now there are two ways we can run our machine code program. We can type sys2061, or we can simply run our basic program. But before we do that, we're going to take a look at an even easier way of doing everything we just did. Remember back in our Visual Studio Code editor, we configured F4 to be the hotkey for assembling our program, but then we still have to load that manually into our emulator, right? We also configured another hotkey, F5, to automatically assemble our program as well as load it into the emulator and open up the emulator for us automatically. So now if I press F5, it should automatically load our emulator. Well, it should first of all assemble our program and then open the emulator and automatically load our program into the emulator. So let's go ahead and see what happens. So there it's assembling it, and now it automatically opens our emulator, and it says that it loaded it into address 0801 to address 0813. So let's do a listing, and you can see there's our program 255 sys2061. And if we change this, I'll just close the emulator again, and now let's change that line number again. Remember, our line number is right here, OA01, which we changed to FF00. So now instead of line number 255, why don't we just make it line number 10 again by changing this to 0A, just to confirm that our process is actually working. So now I'll press F5 again, and we should have our emulator open with our program automatically loaded into it, this time with a line number of 10. Now it's assembling, and it's opening our emulator. It says it loaded our program, and when we do a listing, now we have a line number of 10. Okay, so now that's a pretty easy way to create an assembly language program and automatically load it into the emulator and start up our emulator for us. And now we also know how to use the debugger to explore the memory a little bit, to take a look at the bytes and confirm our program is actually in memory. And of course, there's a lot more you can do with the debugger if you read the instructions and the documentation there. But now it's finally time for us to run our assembly language program and remember what it's supposed to do. Let's take a look at our program again. Right here, it loads the value A6 into the A register. A6 represents that checkerboard pattern in PETSCII, and then it jumps to a subroutine in ROM, which is at address FFD2, which is called char out in the Commander X16 documentation, which prints the character to the screen. So let's go ahead and run our program now by going back to our emulator. And now, like I said, there's two ways we could run it. We could manually type sys2061, because remember, our program is stored in memory at decimal 2061, which is hexadecimal 080D. So I'm just going to type sys2061, and now we should hope to see a checkerboard pattern show up on the screen. And there it is. We have our little checkerboard pattern here on the screen. And another way we could run our machine code program is, of course, just running our basic program, because we do have our basic program in here, right? This line number 10 also executes sys2061. So if I type run, it should also print our checkerboard pattern for us by running our machine code program. And there we go. We have our checkerboard pattern on the screen. So that was pretty fun. As always, thanks for watching, and we'll see you next time.